Good morning, students. Today we are going to have another unit. We are going to start with the third unit about matrices. Of course, probably you would have learned matrices earlier, and matrices are very important, and they are connected with vector space. All the vectors can be represented in terms of matrices, and matrices also can be represented in terms of vectors, especially linear vectors. And matrices, we know about the matrices, which is nothing but the rectangular array of table of numbers, some constants, expressions, which they express the mathematical objects. So, as I said, the rectangular array of a table of numbers. So, either it can be a row numbers or it can be column. So, we have row and column vectors. So, for example, when you take different types of balls, different colors of the balls, which can be represented in terms of matrices easily. Suppose if we have different fruits, so that can be represented in terms of matrices easily. So matrices play a major role not only in mathematics, in all the subjects, statistics, especially in quantum mechanics, probability, and all those numerical methods in computer areas. So it plays a major role. So instead of rectangular array, suppose we are going to have a square array, which is very important in quantum mechanics. So we are going to deal the matrices, especially square matrices. Square matrices will give us determinant. It's one of the properties, and out of this determinant we can get the values of eigenvalues. Eigenvalues are nothing but the roots of the equations. So as I said earlier just now, and matrices are represented in terms of linear algebra. So linear algebra, in which matrices play a major role. We can solve some simultaneous equations. We can get the roots. We can get the solutions. And these are all eigenvalues of the matrices. And as I said just now, this is a square matrix. Square matrix will have non-commuting properties. So which we are going to deal non-commuting properties in quantum mechanics later. So as I said, matrices are very important one, which will play a major role, especially in quantum mechanics. And in this unit 3 about matrices, we are going to deal with the types of matrices, the elementary ideas, the reviews of matrices we are going to deal with, and their properties. We are going to have some review of the fundamental properties of matrices quickly. Under rank of a matrix, conjugate of a matrix, adjoint of a matrix, transformation of matrices, inverse of a matrix, Hermitian and unitary matrices, trace of a matrix, which is very important one, and characteristic equation using matrices, eigenvalue, eigenvectors, Cayley Hamilton theorem, and diagonalization. So those properties are very important, and many of the properties which you have learnt earlier in your UG or in your schoolings. So matrices, just have an introduction. Matrix algebra has at least 2 advantages. As I said, we can solve some simultaneous equations. So it reduces a complicated systems of equations to simple expressions. And second one is adaptable to systematic method of mathematical treatment and well suited to computers. So numerical methods also it is used. And of course we know that these are the type of matrices which we can represent, and this will be your row matrix, and this will be your column matrix, and this is your square matrix, and this will be your rectangular matrix. Okay, we know already about all those things. Okay, a matrix is a set of or group of numbers arranged in a square or a rectangular array enclosed by 2 brackets. The scalar representation, as I said just now, in linear algebra it is most probably it is used to solve some simultaneous equations. We can get the solution, we can get the roots of equations. For example, when you take the scalar representation of any expression, exactly like this. We have not only for 2 by 2 or 3 by 3 or 4 by 4, it goes to n by n matrix. Okay, so we can solve simultaneous. For example, when you take 2x1 minus 3x2 equals 3, minus x1 minus 2x2 equals 6. We can represent this simultaneous equation in a matrix immediately. So matrix 2 minus 3 minus 1, minus 2. Then in a column matrix, x1, x2, which is equal to 3, 6 in a column matrix. We can solve immediately. x1, x2, you bring this matrix to that side, that will give you A inverse. You find the inverse of the matrix and multiply by 3 by 6, that will give you the solution of x1 and x2. Simple idea. Okay, so now matrix representation is given by Ax equals B. So this is called a linear transformation equation. So this equation is known as famous one, linear transformation equation, because we are going to transform from one system to another system. You have a matrix, you are going to multiply with x, and you are going to have another number, another set of numbers. So what we call this as transformation matrix. So for example, you have A array of numbers, array of constants, A11, A12 goes on, and x is nothing but this one, and B is nothing but this one, and we can get a solution. Homogeneous system is B equals 0. Inhomogeneous system is not equal to 0, which is nothing but a characteristic equation. So the trivial solution will be when x equals 0, you will have a trivial solution. So types of matrices, square matrices. So number of rows and number of columns are equal, and we call this as square matrix. Very simple idea. Most probably in quantum mechanics we will be dealing only with square matrices. So if the number of rows and the number of columns in a matrix are equal, then it is called a square matrix. So A equals Aij, M and N. M stands for row and N stands for column. Here M equals N, which is nothing but 3. Okay, M equals 3 and N equals 3. So this is your row, this is your column. 3 rows are there, 3 columns are there. Column, okay, you have a column, vertical one. Rows are like this. 3 by 3 matrix. The sum of the diagonal elements in a square matrix. Very, very important one more question. What is the trace of a matrix? The trace of the matrix is sum of the diagonal elements. So these are all diagonal elements. A11, A12, A13 are diagonal elements. If I equals J, they are all called diagonal elements. See, 1 equals 1, 2 equals 2, here also 3 equals 3. So I equals J. So these termed as diagonal elements. If you are going to add all those things, what we call this as trace of a matrix. So trace of a matrix is adding diagonal elements in a matrix. So trace of a matrix is a summation of Aij, I equals 1 to N, I equals J. So which is nothing but A11, A12, dot dot dot, AN. Okay. Diagonal matrix. Where there exists only diagonal elements alone in a matrix, what we call this as diagonal element. Okay, diagonal matrix. So this is called a principal diagonals. Okay, principal diagonals. So only which we have only diagonal elements alone exists. See 2, 3, 4. All the other things they are 0. Okay, see here they are 0. So it's a diagonal elements. Diagonal matrix. Scalar matrix. So this is your scalar matrix. If diagonal elements are, all the diagonals are equal, this matrix is called a scalar matrix. See here, minus 7, minus 7, minus 7. It can be minus 1, minus 1, minus 1, or 1, 2, 3, 1, 1, 1, 1, or 2, 2, 2, 3, 3, 3. Okay. 1, 1, 1, we will have a separate name, I will say. If all the elements in the diagonal of a matrix are equal, it is called as a scalar matrix. Okay, Aij equal to 0 if I is not equal to j, Aij equals k if I equals j. See, all the elements are equal here. It's a scalar matrix. Unit matrix. So this is what I said. 1, 1, 1 are that, what we call this as unit matrix. If it is 2, 2, 2, what we call this as scalar matrix. Scalar matrix. If it is 1, 1, 1, it's a unit matrix. So every unit matrix is a scalar matrix, of course. Okay, then triangular matrix. A square matrix is said to be a triangular matrix if the elements above or below or the principal diagonals are 0. For example, just take, see, we have diagonal elements. Just above or below, the 0 must be there. Okay, so if it is below, we call this as upper triangle matrix. If it is above, zeros are there above the principal diagonal elements, what we call this as lower triangular matrix. So this will be your upper triangular matrix, this will be your lower triangular matrix. Okay. Singular matrix, very important property while determining the determinant. A matrix is said to be a singular matrix if determinant A equals 0. So if A equals 0, we call that matrix as a singular matrix. If it is not equal to 0, this must be a non-singular matrix. When you are going to take the determinant, A should not be equal to 0. You are going to take the determinant of any matrix which will lead to find out eigenvalues and eigenvectors, and this one should not be equal to, determinant of A should not be equal to 0. If it is equal to 0, it is a singular matrix. Then symmetric matrix. A square matrix which is A equals Aij is called a symmetric matrix if Aij equals Aji. For example, you leave the diagonal elements, you just take these two, so they are equal. You just take these two, they are equal. You just take these two, they are equal. We call this as symmetric matrix. Is it okay? See, A12 which is equal to A21. This is A12. This is A21. A12 which is equal to A21. Similarly, A13 equals A31. So what we call this as symmetric matrices. So next one is skew symmetric matrices. There exists some minus sign. For example, you have 2 and here it will be minus 2. Here it is 1, this must be minus 1. We call this as skew symmetric matrices. So earlier, if they are equal, we call this as symmetric. Suppose if there exists minus sign, we call this as skew symmetric matrix. So Aij equals minus Aj. You bring these two terms here, you will get 2Ai equal to 0. 2 cannot be equal to 0, so Ai must be equal to 0. You are going to add these two, you will get 0. It implies. Okay, this also is skew symmetric matrix. Okay, this one also. So that's the difference between symmetric and skew symmetric. I have given an example. See, A1, 1, minus 1. See, they are equal. Here also it's equal. So what we call this as symmetric matrix, and this is with a minus sign. We call this as skew symmetric matrix. Transpose of a matrix. Transpose of a matrix is you are going to change rows into column or columns into rows. So transpose of a matrix. Transpose of a matrix is very important while determining the inverse of a matrix. Okay, we are going to do to find out the adjoint of a matrix. So this is very important property. So a matrix obtained from a given matrix A by changing its rows into columns or columns into rows. So this is denoted as A to the power T, transpose A to the power T, which is equal to A. We are going to find out now. For example, A is given by this. Okay, this is 2 by 3 matrix. A transpose is given by this. Okay, this is a transpose matrix. Hermitian and skew Hermitian matrices. Hermitian matrix is we are going to transpose first, then take the complex conjugate. Or otherwise, take the complex conjugate and take the transpose. Either way we can do it. That's called a Hermitian matrix. I repeat, we are going to take the transpose, take the complex conjugate, or take the complex conjugate first and take the transpose. Either way the answer will be the same. What we call this as Hermitian matrix. If there exists minus sign, that's a skew Hermitian matrices, which we will say. So we have the notation as dagger. So A dagger. Okay, A dagger represents Hermitian matrix. In quantum mechanics, all the Hermitian matrices will have real eigenvalues. All the operators will be only Hermitian operators in quantum mechanics. Only then we can have real values, real eigenvalues. In order to have real eigenvalues, we must have all the operators should be Hermitian matrix. Okay, Hermitian operators, which we will see later. So for example, you just take this A, B plus IC, B minus IC, D. The first one is, we are going to take the, okay, we will see complex conjugate. We will say complex conjugate. What is the complex conjugate of this? What is the complex conjugate of this? A is a real number. If there is an I, you have to change into minus I. If there is minus I, you have to change into plus I. This is a real number. So what is the complex conjugate of this? A itself. Is it okay? A itself. What is the complex conjugate of this? B minus IC. What is this one? Okay, what? D itself. So first we have done the complex conjugation. The second one, transpose. Just transpose. So this will be B plus IC. You bring this term to here. So this will become B minus IC. The same A itself. This is your capital A. Is it okay? So I have done the transpose, then I have done the complex conjugate. I will get the same matrix. See, A equals A dagger. Is it okay? Clear? Very simple one. Similarly, these are all Hermitian matrices. Just we'll take transpose or we'll take the complex conjugate, doesn't matter, we'll get the same answer. So this will become 3 plus 4i, this will become, take the transpose, see this will become 3 plus 3 minus 4i, then this will become 5. You just take the transpose, so this will come here, this will come here. So this is of the same matrix. Is it okay? So as I said, take the transpose, take the complex conjugate, or take the complex conjugate and take the transpose. So Hermitian matrices will get only real eigenvalues. If a Hermitian matrix or the set of real numbers is actually a real symmetric matrix and A is a square matrix said to be skew Hermitian matrix, as I said, with a minus sign. There exists a minus sign. Okay, if there is no minus sign, we call this as simply Hermitian. If there is minus sign, we call this as skew symmetric. The operation is the same. See, 0 minus 2 plus I. What is the complex conjugate of this? Very good. Minus 2 plus I. Minus 2 minus I. This one will be 2 plus I. Just take transpose. Then with the minus sign. So this will become plus 2. With the minus sign only minus 2. So if you change, you will get this one with a minus sign. So it's a skew Hermitian matrix. Unitary matrix. Unitary matrix we know already, very important property. To simplify the problem, we will use this one. A square finite matrix A is said to be unitary if A dagger A equals I. You check whether this matrix is unitary or not using this condition. Suppose you just consider A is a unitary matrix or not. You have to take the A dagger. A dagger multiplied by A will give you I. 1 0 0 1 or 1 0 0 1 0 or 0 0 1 3 by 3 matrix. Is it okay? So this is a condition. So A dagger equals A star. A dagger A can be written as separately, you can write A dagger A. So A dagger A separately, as I said, separately you can write this as A dagger A, which is nothing but your I, which is nothing but your 1. Okay, 1 matrix. We'll see some problems. This shows that the determinant of a unitary matrix is always a unit modulus, and hence a unitary matrix is a non-singular matrix. We'll see. For example, you just take this matrix A matrix is given. When I'm going to check this matrix is unitary or not, we are going to check. What is the condition? A dagger A equals I. So A dagger A equals I. What is A dagger? A dagger, you will have to take the complex conjugate and transpose. So take the complex conjugate and transpose. What is the complex conjugate of this? Minus I by root 2. This will become minus I. This will become plus I. These two are as it is. Now take the transpose. So this will become plus. So this is C plus. This will become minus. See here, plus minus. And these two things are same. Simple idea. So now A dagger A equals A dagger you have found out already. So A dagger multiplied by the matrix multiplication multiplied by A. You are going to multiply these two. So when you are going to multiply these two, you will get this one multiplied by this one. Correct? So this multiplied by this. 1 by root 2 multiplied by 1 by root 2 will give you 1 by 2. I by root 2 multiplied by minus I by root 2. I squared minus 1. So plus 1 by 2. 1 by 2 plus 1 by 2 is nothing but 1. Is it okay? I repeat. 1 by root 2 multiplied by 1 by root 2. Answer is 1 by 2. Plus I by root 2 multiplied by minus I by root 2. Minus I squared by 2. I squared is minus 1, so plus 1 by 2. Already 1 by 2 is there, so 1 by 2 plus 1 by 2 will give you 1. Similarly, you can go for the next element. So this is nothing but your I. See, I. So that's a condition. So when you are going to prove this matrix is unitary or not, you will have to use A dagger A equals I. Is it okay? Now we will go for trace of a matrix. So there are three properties of trace of matrix which are very important. We have already discussed about the trace of matrix earlier, which says that adding the diagonal elements. Very important, one more question. Adding the diagonal elements. You are going to add all the diagonal elements. Okay, we are going to add all the diagonal elements. For example, in a matrix you have 1 0 0 1 0 1 0 0 0 1. What is the diagonal element for unitary matrix? 3 by 3 matrix. Answer is 3. That's all. For 2 by 2 matrix, answer is 2. That's all. We are going to add all the diagonal elements. So three properties are very important property. Trace of lambda A. A is a matrix. Lambda is a scalar number. So I can pull lambda out. Lambda trace of A. Trace of A plus B equals trace of A plus trace of B. So these are all properties. Trace of AB equals trace of B. You have to reverse and do the operation. So these properties are very important. Then some more properties are there. A transpose of a transpose is nothing but A itself. Okay. Lambda A to the power T equals, you pull lambda, so lambda A to the power T. Lambda being any scalar. It can be a real number or a complex number. A plus B to the power T equals A to the power T plus B to the power T. Individually you can do. What we call this as compatible for addition. Similarly for multiplication. Very important thing here is AB to the power T equals B to the power T and A to the power. It is not A to the power T, B to the power T. Very important one. So this is for the multiplication. That's a property. We can check easily. No worries, we can check easily. Okay. So this is for the multiplication. So these are the properties for traces. Orthogonal matrix. So earlier we discussed about A dagger A equals I. Can you remember? To find out the unitary matrix, just go with A dagger A. Similarly, another condition is to find out the orthogonal matrix A dagger equals I. Suppose A is an orthogonal matrix. You just take the transpose. Multiply these two. You will get identity matrix. So what we call this as orthogonal matrix. So both the matrices are perpendicular to each other. We will solve some problem. It's very easy. Okay. So the condition is A dagger A equals I. A T is a transpose of a matrix of A. I is a unit matrix, identity matrix. So A T A equals A T, individually you can write. Okay. And just now we said A T equals A. So instead of A T you can write A itself. So you will get A square equals 1. So you will have A equals plus or minus 1, which are nothing but your values. So these are the values, like eigenvalues. This shows that determinant of an orthogonal matrix can only have values plus 1 and minus 1, which we'll check already. Okay, which we'll see now. The properties of complex conjugate of a matrix. Complex conjugate. We are going to take the complex conjugate of any matrix. So if there is I, you will have to write minus I. If there is minus I, you will have to write plus I. So this is called complex conjugate. The complex conjugate of an arbitrary matrix A is formed by taking the complex conjugate of each element. So each element we are going to take. Okay. What are the properties of complex conjugate? A star equals A means if matrix is real matrix. If A star equals A, for example, just take 2. 2 is a real number. Okay. What is the complex conjugate of this? Again 2 itself. So it's a real matrix. So real number. Suppose there exists 1, 2, 3, 4, 2 by 2 matrix. Take the complex conjugate. The answer is that matrix itself. 1, 2, 3, 4. Correct? 2 by 2 matrix. So it's a real matrix. Real matrix. A plus B whole star equals A star plus B star. So this is comfortable addition. And lambda A star can be written as lambda star A star. Lambda can be a complex number. If it's a complex number, then we will have to change. If there is a real number, no need to change. It depends on lambda being a complex number or real number. Then AB dagger, as I said, B dagger, A dagger. Okay. Properties of Hermitian conjugate. So A dagger, which is denoted as Hermitian. Okay, Hermitian is denoted as A dagger. A dagger is nothing but you take the complex conjugate and take the transpose, or otherwise take the transpose and take the complex conjugate. What are the properties? A dagger of dagger equals A. A dagger of dagger. Okay, you are going to take the complex conjugate, take the transpose, again take the transpose and take the complex conjugate, you will get the same matrix A itself. Okay, so A plus B whole dagger equals A dagger plus B dagger. Lambda A dagger is nothing but lambda star. Okay, but usually for any operator we will go only with the lambda dagger. Suppose if there is an operator, here lambda is a number, complex number, only then we can go with complex value. Suppose if it is an operator, then we'll have to write lambda dagger. Okay, this is notation followed in quantum mechanics. So lambda star A dagger, lambda being a complex number. Similarly, A B dagger is nothing but B dagger A dagger. Okay, so this is comfortable bar multiplication. Now we'll solve some problems. Show that the following matrix is orthogonal. So what is the condition for orthogonal? A dagger equals, okay, identity matrix. We will get 1. Okay. So this is the matrix is given 0 1 0 1 0 0 0 0 1. What is A transpose? 0 1 0 1 0 0. Then the last one is 0 0 1. Now you have to multiply these two. So A dagger. You are going to multiply these two. So this is your A, this is your A dagger, matrix multiplication. So you will have to multiply this and plus this plus this. That is 0 plus 1 plus 0. First element. Second one will be you will have to multiply this one by this one and add. And third one will be you have to multiply this and add. Okay. So adding all those things, that will give you 1 0 0 0 1 0 0 0 1, which is nothing but your identity matrix, unit matrix. So A dagger equals I. Okay.